Alright guys, so today we're going to talk about implicit differentiation. So what is it and when do we use it? Well, what we've been doing so far is we have an expression, say, y equals x squared plus 7x minus 2. And we take the derivative, right? So y prime then happens to be 2x plus 7. Okay? And that is going to be our derivative. So easy. But what happens then if we have something like let's say the equation of the unit circle. And now you want to find right there the derivative of y, so y prime. How do you do that? So what we're going to do is we're going to do the chain rule to compute this. So what I'm going to do is I'm going to take the derivative with respect to x on both sides. And I get the derivative of x squared is going to be 2x plus the derivative with respect to x of y. I don't have the derivative with respect to y, but what I can do is I can take the derivative of this with respect to y, and then I pay with the derivative of y with respect to x. That's going to be the chain rule applied to this expression. You're taking the derivative of, say, the outside function is y, and then you pay with the derivative of the inside, which is going to be derivative of y now with respect to x. So when you do that and continue to take your derivatives, derivative of 1 is 0, you can then compute dy by dx by computing this derivative. Derivative of y squared with respect to y is going to be 2y times dy dx, that one I cannot do anything about it, equals 0. Now this dy dx is also called y prime. So what I have to do now to find my derivative is to solve for this expression here. I'm not going to call it y prime, even though it's easier to write it, because sometimes it gets a little bit confusing when you have y prime and you forget which one has the prime or not. But I'm going to write it as dy dx just because it makes it a little bit easier. So I'm going to start by subtracting 2x on both sides. I get 2y dy by dx, if you like y prime, that's y prime, equals negative 2x. Divide both sides by 2x, 2y rather, and you get that dy by dx is going to be equal to the 2's cancel, and you get negative x over y. And right there you have that y prime, if you want, is going to be equal to negative x over y. So now your derivative, in contrast to what we had before, does not just depend on x. It depends on x and y. But if you want to find the derivative at a point, say you're given a coordinate x comma y, you can certainly evaluate it there. So let's say we needed to compute this at one point in the unit circle. The unit circle here, you have x squared, y squared equals 1. One point in the unit circle, for example, 1/2 comma square root of 3 over 2. Then you get that your derivative happens to be x, which is 1/2, well, negative first, 1/2 over the square root of 3 over 2, which is the same as negative 1/2 times the conjugate of 3/2, which is 2 square root of 3, and that the 2's cancel, and you get 1 over square root of 3. And I ate a negative here. There it is, negative. And of course, you could rationalize the denominator if you prefer. I like to leave it like that because that's perfectly fine in my opinion. But you could still rationalize the denominator. All right, we're going to do a couple more, and we will now use an easier approach. This one may have been a little bit confusing in this part. So I'm going to do it a little bit easier, and that's going to be the way you will normally compute it whenever you have a problem. So let's go ahead and do that. All right, So let's go ahead and compute another one. So let's do something like x cubed plus 2xy plus y cubed equals 5, let's say. Something like that. And let's compute that derivative. So we're going to go ahead and start by taking our derivative on both sides with respect to x. And I'm writing it not just the prime, so it reminds me that I'm taking derivatives with respect to x. Because I have two variables now, so I have to be mindful of which one I'm taking the derivative of, or with respect to which variable I'm taking the derivative, rather. And here, I get the first one is easy, so just derivative of x cubed, so do 3, so drop the exponent, copy the x, and subtract 1. Now here, you have a product of variables, so you have to do the product rule. So you're going to take the derivative of, and I'm going to separate this into two terms. I'm going to do colors to separate it. I'm going to collect the 2x here. That's going to be one term, and my other term will be y. So whenever I'm taking the derivative, I'm going to put in parentheses so you keep track of it. Derivative of the first, that's going to be 2x, just 2, derivative of 2x, just 2, sorry. And then times the second, so derivative of the first times the second. So what I did there was, this is going to be the derivative of the first. I copy the second. All right, so far so good. Now the next one, the next term usually causes some trouble. Copy the first. And then you have to multiply times the derivative of the second. And in this case, the second one is y. And so the derivative, I'm just going to write dy dx. Why? Because I'm taking the derivative with respect to x, not with respect to y. All right? So that's going to be that middle term. Then I'm going to have the next one, which is going to be the derivative of y cubed. The way we're going to do this, we take the derivative of y cubed, so 3y squared, but I'm not taking the derivative with respect to y. I'm taking it with respect to x. So I'm going to pay with dy dx. That's the chain rule right there. You take the derivative of the function as if it be with respect to y, but you pay with dy dx. And then you set it equal to derivative of 5, which is 0. One very common mistake that happens in these problems, when you take the derivative of this term, you forget you're taking the derivative and you just write equals 5. That makes it a disaster. So let's try to remember what I'm trying to do here. I'm trying to solve this for dy dx. So I have two of them. So what I'm going to do is everything that has dy dx, I'm going to put on the left side. And everything that does not have a dy dx, I'm going to move to the right side. So the way I'm going to do that, these two guys are already here. I'm going to subtract this guy on both sides. That takes him over here. This right here, I'm going to subtract it as well. When I do that, I'm going to have just the terms that survive are going to be 2x dy by dx plus 3y squared dy by dx is going to be equal to negative 3x squared minus 2y. Okay, so that is good because I'm trying to solve for dy dx. And whenever you're doing your implicit differentiation, at least when you're computing the first derivative, this is always going to be a linear equation with respect to dy dx. It doesn't look like it's linear, does it? You have x's, you have squares and y's and all sorts of things going on. But if you think about this as a times, say, y prime plus b times y prime equals c, that is an equation that is linear. What you're going to do then, you're going to factor that dy dx. And you're going to leave this side alone. And then you're going to divide both sides by this expression. And you're going to get that the derivative is going to be negative 3x squared minus 2y all over 2x plus 3y squared. All right, so that right there gives us our derivative. And the steps are always going to be the same. Step 1, take the derivative with respect to x on both sides. Step 2, when you're taking the derivative of any y, what you're going to do is you're going to pay, remember to pay, with dy dx. Then 3, collect all terms involving dy dx on one side and I'm not going to write this because it'll take too long, and move the other ones to the other. 4, factor dy dx, and then 5, divide by whatever the expression that multiplies dy dx. That is just to solve. So right here, if we mark our steps, step 1 is here. You're taking the derivative. Step 2, I'm remembering to pay with dy dx whenever I find a y. All of the other rules of differentiation still apply. Step 3, collecting all terms on left-hand side that have dy dx and the other ones to the right. Step 4, factor right here. And step 5, divide to solve. It's always going to follow those steps, and so it can get confusing at times if you don't do it in a very organized way. So let's solve a couple more, and I think that's going to wrap it up for this video. All right, so let's do another example here. So let's do, for example, the sine of x over y equals cosine of y over x. It's a little bit more complicated, isn't it? Yeah, a little bit. So let's take a look at what happens. So first, take our derivative. Derivative on both sides. And so what do we do now? Well, we take our derivative using chain rule. So derivative of left-hand side is going to be derivative of the sine is going to be cosine. We're going to leave it x over y. That's going to remain there. Times the derivative of the inside. So I'll do it in a lot of steps here because it's, even though it's a short problem to us, there's a lot of things going on in it. So now with the derivative of the cosine, we get negative sine evaluated at the inside, y over x, times the derivative of the inside. That's our chain rule. All right, so we get that right there. And now we have to take this derivative. That's going to be a quotient, so we'll do quotient rule. So we're going to have cosine x over y, and then we get times, and we get derivative of the numerator, which is 1, that's right, 1, times the denominator, y, minus, then we get derivative of the denominator, dy by dx, times the numerator, so x dy dx, all over the denominator squared. So the same thing here. So I'm probably going to run out of space, so maybe I'll place it down here, unfortunately. can I fit it there? Maybe if I write small. Ill decision there, but let's go for it. So we get derivative of the top times the bottom, or derivative numerator times the denominator, is going to give us an x dy dx. Minus derivative of the denominator, which is 1, times the numerator, so y, all over the bottom squared. So for all of those who were doubting that it was going to fit, there it is. It's definitely a lot smaller, but we got it. All right, so this is looking like an absolute mess. So what I'm going to do is follow my procedure. I'm going to collect all terms a little bit, but my goal is to move dy dx to, in this case, the left side. So all of the dy dx's, I'm going to move to the left. So to do that, first I'm going to distribute here all this mess. So for example, here I get cosine times y divided by y squared. I'm just going to get cosine all over y, so I can just write 1 over y. So that's the first term. I distributed this term. I have to divide this one as well. Minus, I'm going to have a cosine of x over y. And then I'm going to multiply times x over y squared times cosine times dy dx. So where do we put the x, and the y squared would have been good here, but now I'm going to put it here. All right, so now I'm going to have to expand this one, so I'm going to now go to a second line. So I'm going to do, when I distribute this one here, I get an x cancel, so I get 1 over x, negative 1 over x, sine of y over x times dy dx. So that when I distribute this term here, I have to do the same here. So I'm going to have minus negative, so plus, sine, and let me copy the y over x squared in front. Y over x. So it looks like an absolute mess, but we're doing the same thing we did before. I'm going to collect these two guys on the left-hand side of my equation. So those terms will go there, and let's use a different color. This term here and this term here we'll put in the other side of the equation. So that's going to be my first step. I'm not going to write what I have to subtract and all because it's going to get really messy, but I'm going to add this term on both sides to cancel. That's going to give me 1 over x sine of y over x dy dx. And then here I'm going to have minus x over y squared cosine of x over y dy dx equal to, can I fit it all? I hope so. So I'm going to copy this guy right here, y over x squared sine of y over x. And then I'm going to subtract this guy here. I'll put it down in the next line. Minus 1 over y cosine of x over y. Okay, so this is starting to look a little bit better, even if you don't believe me, because now I have dy dx together. So I can factor that guy out, and I'm going to have 1 over x sine of y over x, so that guy, minus x over y squared cosine of x over y, the whole thing multiplied times dy dx. And that's going to be equal to this other expression, y over x squared sine of y over x minus 1 over y cosine of x over y. And now it's just a matter of dividing this whole expression by this. We would have to do a common denominator and simplify, but I think it's good enough to explain to you or to show you that you just have to follow the steps no matter how ugly the expression results. So copy this expression here. All over this expression here. And then x over y squared. Ooh, I dropped the square here. You see, it has to be symmetric because of the way we wrote it. So x over y squared. I noticed there was a problem there. We fixed it already. So cosine x over y.